This video is prepared by Aavya classes. Please subscribe the channel, raise your doubt and watch the video for sure success in JEE, AIIMS and NEET.
Hello friends, in this video you will learn following topics: lens maker formula, effect on focal length, and if lens is placed in a different medium. So if you place a lens in different medium, then what will its effect on the focal length of lens? We will also see different cases of placing a lens into medium and how the nature of lens changes sometimes if we place it in a medium. We will also see the dependence of focal length on color of light. We see that when lens is made of layers having different refractive index, then what will be the focal length in that case? And if both side of lenses have a different medium, then what will be the focal length of lens? And this is especially very important topic. We will also see some numerical based on the lens maker formula. So it's important to watch this video from start to end, and please submit your feedback. Feedback are very valuable to us. Keep watching and happy learning. Now we will see lens maker's formula. So basically it's a lens maker's formula which give you an idea of the focal length of lens. It's lens maker's formula. So the relation between F, mu, R1 and R2 is known as lens maker's formula, and it is as 1 by F is equal to mu lens divided by mu medium minus 1, and it is multiplied by 1 by R1 minus R2. This is the lens, then the radius of its first surface is R1, the radius of its second surface is R2. If the refractive index of this lens is mu L and the refracting index of this medium is mu medium or mu M, then the focal length of this lens, or the inverse of focal length of this lens, is equal to mu lens divided by mu medium minus 1 into 1 by R1 minus R2, and we may write it also medium mu lens minus 1, that is the refractive index of lens with respect to medium, minus 1 into 1 by R1 minus 1 by R2. So what is meaning of this medium mu lens? So it's a relative refractive index. We have already covered this concept of relative refractive index in my section of refraction, A mu G. So we usually say that the refractive index of glass is 3 by 2. So it is the refractive index of glass with respect to air. So basically it's mu G divided by mu A, that is the refractive index of glass with respect to air, is equal to 3 by 2. Now if we place the same glass into water or same lens in water, then its refractive index will be changed to W mu G, that is mu G by mu W. And it says that the refractive index of glass with respect to water, and it is equal to 3 by 2 divided by 4 by 3, that is it is equal to refractive index of glass with respect to air divided by refractive index of water with respect to air, and from there we get the value of it is 9 by 8. So refractive index of glass with respect to water, that is the relative refractive index of glass with respect to water, is equal to 9 by 8. So if lens is placed in a medium having refractive index mu, then 1 by F is equal to medium mu lens, or the refractive index of lens with respect to medium, minus 1 into 1 by R1 minus 1 by R2. And it is important to note that the sign is not been taken in the consideration. So you have to apply the sign after writing this formula. So all things are written here, where medium mu lens is the refractive index of lens material in the medium having refractive index mu medium. And if the medium is to be air, then 1 by F is equal to mu minus 1, 1 by R1 minus 1 by R2. Now we will derive this formula. So for this we have taken a convex lens. You can take any lens. This formula is equally true for any kind of lens. We have taken the convex lens in order to make the ray diagram easy. We have taken it for our convenience. So if O be the object, then first the light ray comes, hit this first surface. So this is the first surface, this is the second surface, and as we know that the refraction through any surface, any curved surface, is given by the formula mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r, where mu2 is the medium in which light ray is going, and mu1 is the medium from which light ray is going. So and r is the radius of curved surface. So, and we know that if the light ray goes from rarer to denser medium, then it moves towards the normal line. If it moves denser to rarer medium, then it moves away from the normal line. So the radius of this surface will be supposed in this way. So it will move towards the normal line. It will move in that way. It will move in that way towards the normal line. This is the normal line. So the angle of incident, if it is I1 and this angle is R1, then R1 must be less than I1. So we get a image due to this refraction at the point we call it I1. So the image I1 will be formed if the second surface would not be there. However, as we have second surface also, so we get the refraction from that surface also. So considering this as the normal line for the second surface, then the light ray move away from the normal line, and here if you see, this is our angle of incident I2 and angle of refraction will be more, and the light ray will hit the principal axis at this point, we call it I. So basically I will just draw the ray diagram here also. This goes in that way, afterwards it move here, and then it moves in this way because this is the normal line, and so the angle of refraction R2 must be greater than angle of incident at the second surface I2, as the ray is moving from denser to rarer medium. Now we have to consider this as a thin lens. So this formula is applicable only for the thin lens, and this is our assumptions for this formula. Consider this point as P, this point as Q, and the optical center of this is C. So this is our object distance. So this is our basically object distance for this first surface, and the image distance is equal to, that is Pi1 is V. So consider it's V1. In fact, object distance OP is equal to U, and the image distance Pi1 is V1. The radius of this first surface is R1, and it should be taken as a positive sign, as the direction of incident light ray is taken to be positive. Now we will apply the refraction formula for the first surface. So the formula is mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. So for first surface, the mu2 is equal to mu l, and the image distance is equal to Pi1. The mu1 is equal to mu medium, as the light ray is going from medium having refractive index mu m. So mu m divided by, and u is equal to Po is equal to mu l minus mu m divided by R1. R1 comes with a positive sign here. Just write this equation considering that there is no second surface. So if there is no second surface, then the image of this object would have formed at the point I1. Now we Now, due to second surface, the light ray again refracted and the final image is formed at the point I. So, for second surface, for refraction from second surface, we have to write the equation. Again, we will first write our basic equation, mu 2 by v minus mu 1 by u is equal to mu 2 minus mu 1 by r. And then if I put the value, then mu 2 is medium in which light ray is going. So here light ray is going into medium having refractive index mu m. So mu m, and the final image is formed at this point. So this is our final image formed. So this is qi, we call it V. So QI, obviously it comes with a positive sign, as this is the in the direction of incident light ray, and all distance are measured from this point. We call this point as pole. So all distance are measured from point Q. So it's a QI comes with a positive sign. Minus mu 1 is mu L divided by U is equal to QI1. So again, it also comes with a positive sign. See, this I1 serves as a virtual object for this second surface. So I just write it here that I1 serves as virtual object for second surface. So clearly the object distance for the second surface is equal to qi1, and if I put the value for the right hand side, then it's equal to mu m minus mu l divided by minus r2. So clearly if you see here, R2 is in the direction opposite of incident light ray. The radius of curvature for this second surface is on the left hand side, and we have already taken the right hand side as positive. So the equation will be mu m by qi minus mu l by qi1 is equal to mu m minus mu l divided by minus r2. So this is our equation 2. Now the image is formed due to refraction from first surface and second surface both. So we have to consider the equation through both surfaces. We have to consider the contribution through both surfaces, and for this we just add equation 1 and equation 2. So if we add equation 1 and 2, so adding equation 1 and 2, we get mu L by Pi1 minus mu L by Qi1 plus mu M by Qi minus mu M by Po is equal to mu L minus mu M 1 by R1 minus 1 by R2. So this is our equation 3. Now we are considering this as a thin lens. So this formula, the lens maker formula, is valid only for the thin lens. So for the thin lens, we consider PQ approximately equal to 0, and in this way we can write PO is equal to QO, and it is equal to CO. So we are considering the all distances from the optical center. So that's why PO is equal to CO and it is equal to QO. And similarly we may write QI is equal to CI is equal to PI, and again QI1 is equal to CI1 is equal to PI1. So we are considering it as a thin lens. So if we apply this concept, then Pi1 is equal to Qi1 and it is equal to Ci1. So this first term will get cancelled out. So this term will cancelled out and we get mu m 1 by Qi minus 1 by Po is equal to mu L minus mu M 1 by R1 minus 1 by R2. So clearly 1 by Qi is equal to 1 by V. So 1 by V minus 1 by U is equal to, basically if you see here that PO is equal to CO and it is equal to U, and Pi is equal to Ci and is equal to V. So 1 by V minus 1 by U is equal to mu L by mu M minus 1 into 1 by R1 minus 1 by R2. Now we'll see a case when object is placed at the infinity. So when object is placed at infinity, that is u is equal to infinity, then we know that by the formula 1 by v minus 1 by u is equal to 1 by f of length formula, that 1 by v minus 1 by infinity is equal to 1 by f, and from there we get 1 v is equal to f. So if we put the value of u is equal to infinity, we get v is equal to f, and from there we get 1 by f is equal to mu l by mu m minus 1 into 1 by R1 minus 1 by R2, and this is our lens maker's formula. So this is one of the important formula for the examination viewpoint, whether it's JEE Mains or class 12 or NEET, AIIMS or AIEEE, and you have to understand this formula, you have to understand the application of this formula. So now we understand the application of this formula. Now we see the applications of lens maker's formula, and here mu is the refractive index, where mu is the relative refractive index of lens, that is mu lens minus mu medium. So if I write mu, then it means it's mu lens divided by mu medium. So first is the biconvex lens, and if it is equiconvex lens, then R1 is equal to R and R2 is equal to minus R, that is the radius of both sides are same. So consider a general equation of biconvex lens. So first thing is that you should know how to apply the lens maker formula after taking sign also in consideration. So here we know that 1 by f is equal to mu length divided by mu medium. We call it mu minus 1 by r1 minus 1 by r2. So for a biconvex lens, if the light ray is coming in this way, suppose the light ray comes in this way, then this direction is taken as positive, this direction is taken as negative. So in this way we may write R1 is equal to plus R and R2 is equal to minus R, because the radius of this surface is towards the direction of incident light ray, while the radius of second surface is opposite to the direction of incident light ray. So from there we get mu minus 1, and considering the both radius as same, then 1 by r minus 1 by minus r, that is mu minus 1 into 2 by r. So f is equal to r by 2 into mu minus 1. So considering the lens made of glass and placed in air, so if we consider mu L is equal to 3 by 2 and mu medium is equal to 1, that is A mu Z is equal to 3 by 2 and it is equal to mu, then the equation will be changed to F is equal to R divided by 2 into 3 by 2 minus 1, and from there we get F is equal to R. So the focal length of that lens will be equal to radius of each curvature. So F comes equal to R in that case. Now if I place that lens into water, so if lens is placed in water. So if you place the lens in water, then the mu will automatically change to mu lens divided by mu water. So in that case, mu lens is 3 by 2 and mu water is equal to 4 by 3. So from there we get 9 by 8, and 1 by f is equal to 9 by 8 minus 1, 1 by r minus 1 by minus r. So we get 9 by 8, it is 1 by 8 into 2 by r. So focal length will be changed to r, focal length will be changed to 4r. So you see that the focal length changed by 4 times. So if a same biconvex lens is placed in water, then the focal length of that lens becomes 4 times. That is, focal length increases drastically and its power decreases. Now we will see the second concept, that if the light ray is coming from this way, that is, if the light ray, instead of first time the object we placed at the point O, now we place the same object at point O1. So if we place the object at point O1, then the incident light ray moves in this direction, and then we calculate the value of focal length by using lens maker's formula. So 1 by f is equal to mu minus 1, and here if you see that r1 is equal to r2, and r2 comes with a positive sign because the direction of r2 is in the direction of incident light ray. So 1 by R2 minus 1 by R1. So from there we get mu minus 1 into 1 by R1 plus 1 by R2. So there is no any change in the lens maker's formula whether the object is placed on the left side of lens or on the right side of lens. So these are the two concepts. First, the focal length remains same if we place the object on the left or the right hand side, and if we place the lens in a medium different from air, then its focal length changes. If we place the same lens in water, then its focal length becomes 4 times. Now we will see plano-convex lens. So plano-convex lens has one surface as a plane surface. So we will again apply the lens maker's formula in that case, and suppose the light ray is coming from this direction. So 1 by f is equal to mu minus 1 into 1 by r1. So again r1 comes with positive sign, and the radius of curvature for the plane surface is infinity. So minus 1 by infinity, and from there we get mu minus 1 into 1 by r1. So considering r1 is equal to r, we get mu minus 1 by r, and from there we get focal length f is equal to r by mu minus 1. So if I take mu is equal to 3 by 2, that is, if you place the plano-convex lens in air, we get f is equal to r divided by 3 by 2 minus 1, that is 2r. If the same lens is placed in the water, then fw is equal to 4 into 2r, that is equal to 8r. Now we will see again if the object is placed on the other side. If the object is placed on the other side, then apply the lens maker's formula. 1 by f is equal to mu minus 1. Suppose this is the object we place at O1, then first this we have to consider this radius of curvature, and this radius of curvature is infinity minus 1 by minus r1. So we get the formula is equal to mu minus 1 by r1. The formula remains same. So for the plano-convex lens, length of focus is r divided by mu minus 1. Now we will see third type of convex lens, that is concavo-convex lens. So I will first draw the figure of concavo-convex lens, and then we will apply the lens maker's formula on that lens. So this is our concavo-convex lens. If you see this lens, then this is thick in middle than the periphery, and the first surface is convex surface and the second surface is concave surface. the radius of curvature of concave surface is more than the radius of curvature of convex surface. That is, in other way we can say that in case of concavo-convex lens, it has a steeper convex surface than concave surface. So this is a more steep curve. So this is the steeper curve, and if we consider its radius as r1, its radius as r2, then R1 is less than R2. And if I apply the lens maker's formula, then 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2. Here R1 and R2 both comes with a positive sign. If I place the object at this point, then the light ray goes in this direction, and this direction is taken as positive. So clearly R1 and R2 both comes with a positive sign. So it's a mu minus 1, 1 by R1 minus 1 by R2. And again, as R1 is greater, the R1 is less than R2. As R1 is less than R2, so 1 by R2 is less than 1 by r1, and from there we get 1 by r1 minus 1 by r2 must be greater than 0. So 1 by f is equal to mu minus 1, and we consider it 1 by d, that is 1 by d is equal to 1 by r1 minus 1 by r2, and it's a greater than 0. So we get 1 by f is greater than 0. So basically focal length in this case comes with a positive sign. We call it as a positive meniscus lens. So concavo-convex lens is a positive meniscus lens due to its positive focal length, and because of this it has an ability to converge the light ray. While if you see later on that in case of convexo-concave lens, that is this is our concavo-convex lens. Concavo-convex lens, these are used in the corrective lens. So here the focal length comes with a positive sign, and in case of convexo-concave lens, where we have a steeper concave surface, the focal length comes with a negative sign. So now what will be the case if I place the object at this point? So suppose if I place the object at the concave surface side and then apply the lens maker's formula, then 1 by f mu minus 1 into 1 by, or if the light ray comes from the concave side, then 1 by r1, r2 comes with a negative sign, so minus 1 by r2 minus 1 by r1. So we get it's mu minus 1 into 1 by r1 minus 1 by r2. So it's the same as the previous case. So wherever the object is placed on the convex side, wherever the object is placed on the concave side, the result becomes same if we apply the lens maker's formula. So I think this concept is clear to you. Now we will move to our next concept, that is if the lens maker's formula is applied to concave lens, and here we will do it a bit fast, that as we have already learned the most of the concepts. So if I apply here, if you see here, r1 comes again with a negative sign, and r2 also comes with, and r2 comes with a positive sign. So it is the object, the light ray moves in this direction, and after refraction it is moving to the denser to rarer medium. So suppose this is the incident light ray, so it goes in that way, and afterwards this is here the incident light ray, so it goes in outside. So basically it's a diverging lens, and we get that the formula 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2, where mu is mu lens divided by mu medium. So mu minus 1, I just note it, write it there, because sometimes people get confused. 1 by r1 minus 1 by r2. So mu minus 1 into 1 by r1. R1 comes with a negative sign, so minus 1 by r, as the direction of radius of curvature for this surface in this way, and we are taking this direction as a positive, this direction as a negative. So minus 1 by r2 is equal to plus r. So we get mu minus 1 into 2 by r with a negative sign. So it's basically f is equal to r divide minus r divided by 2 into mu minus 1. Now if we take the refractive index of glass as 3 by 2 and the lens is placed in air, then f comes equal to minus r divided by 2 into 3 by 2 minus 1, and it's minus r divided by 1 by, so its value is equal to minus r. So if you see here, the focal length of lens comes out to be negative, and because of this we can say that the concave lens is diverging lens. Again, if you place this concave lens in water, then the focal length becomes 4 times, so fw is equal to minus 4r. So, so this is all about equiconcave lens. If we consider the plano-concave lens, then 1 by f is equal to mu minus 1 into minus 1 by r minus 1 by infinity, and we get mu minus 1 divided by r. So minus mu minus 1 divided by r, and f is equal to r divided by minus mu minus 1. So if I put the value of mu is equal to 3 by 2, then the value turns out to be minus 1 by 2, that is equal to minus 2r. So again it comes with a negative value, so it's a diverging lens. Always if you get the focal length negative, then it's a diverging lens, and in that case also you see that the power of lens becomes negative. That's why the power of a convex lens is positive, power of a concave lens is negative, as the power is reciprocal of focal length. So in the market also, if you go there, they ask your the power of your lens, and if you say plus sign, then it's a converging lens you are looking for, and if you say negative sign, then you are looking for a diverging lens. So the same lens, if it is placed in water, then the value comes out to be minus 4 into 2r, that is minus 8r. The focal length of a plano-convex lens becomes 4 times if you place this lens in water. Now the third case is the convexo-concave lens. Convexo-concave lens. We call also it convex concave lens. So as we know that the convexo-concave lens has a steeper concave surface, while the convex surface has a larger radius of curvature. So I will show it first, then so this is our concave surface. So this is our concave surface, and this is our convex surface, and the radius of curvature of this surface is, if the radius of curvature of this surface is r1, and this surface having radius of curvature equal to r2, then r1 is less than r2. So basically it has a steeper concave surface, and the radius of curvature of convex surface will be more. So this is our convex surface, this is our concave surface. Now if I apply the lens maker's formula, suppose the object is placed at this point, we call it O, then 1 by f is equal to mu minus 1 by r1 minus 1 by r2. Now if you see here, r1 comes with a negative sign, r2 also comes with negative sign. So mu minus 1 into minus 1 by r1 minus 1 by minus r2, as this is the direction of incident light ray, and it comes with positive, this comes with negative. So it's equal to mu minus 1 by r2 minus 1 by r1. So as r2 is greater than r1, so 1 by r2 is less than 1 by r1, and from there we get 1 by r2 minus 1 by r1 less than 0. So 1 by f is less than 0, and f comes with a negative. So f is a negative quantity, because of that it diverges the light ray. So basically we call it as a negative meniscus lens. Negative meniscus lens, and it is also used as a corrective lens. So I think we have already learned the lens maker's formula. We have already applied the lens maker's formula on different type of lenses. Now we will learn more about it. Concept is the ratio of focal length. So if lens is placed in a air and in a different medium. So as we know that if a lens is placed in air and if the radius of curvature is 1 by r1 and r2, then the focal length is 1 by fa is equal to mu minus 1 by r1 minus 1 by r2. And if same lens is placed in any other medium, then 1 by fl is equal to, here mu is equal to mu z. So basically if we write it a mu z, so that is refractive index of glass with respect to air. So 1 by fl is equal to mu l divided by mu medium. So suppose this is medium 1 by fm. So mu L divided by mu medium minus 1 by R1 minus 1 by R2. So if I divide these two terms, then it's a fm divided by fa is equal to a mu g minus 1 divided by m mu g minus 1. Ratio of focal length of lens in a medium having refractive index mu m and in air is equal to a mu z minus 1 divided by m mu z minus 1. So this concept is written here, and if a lens is placed in a water, then the ratio of focal length will be, so here if we place the lens into water, then we have to write the ratio of focal length. So here a mu z is equal to 3 by 2 minus 1 and W mu z. So we have to calculate first W mu z, that is the refractive index of glass with respect to water, and it is equal to 3 by 2 divided by 4 by 3, that is equal to 9 by 8. So 9 by 8 minus 1, and from there we get 1 by 2 divided by 1 by 8, that is equal to 4. So FW is equal to 4 FA. That is, if you place the lens in water, then the ratio of focal length of that lens in water and air become 4 times. So focal length of glass lens in water increases by 4 times. If f with the focal length in air, then inside the water its focal length becomes 4f. So as the power is inversely proportional to focal length, then the power of same lens decreases. So conclusion is, in liquid focal length of lens increases and its power decreases. This is true in case of following, that is when the refractive index of medium is greater than air but less than the refractive index of glass. So if mu m be the refractive index of that medium, then it must be greater than the refractive index of air, and it's quite true because all things having the refractive index more than air, and but it should be less than the refractive index of glass. So till the time this condition holds, then the focal length of lens increases and its power decreases. So if you place a lens in a medium whose refractive index satisfies the criteria 1 mentioned here, then the focal length of lens increases and its power decreases, as power is the inversely proportional to focal length. Now if we place same glass lens in a glass medium, that is we are keeping the refractive index of medium and lens equal. So if mu m is equal to mu z, so in that case the focal length becomes infinity, the converging or diverging power of lens becomes 0. So it will then act as a plain sheet of glass. So based on these concepts, a small concept, we just generalize our theory of different cases of placing a lens into a medium. So depending on the refractive index of lens and the medium, following three situations are possible. That like first situation is that if we place the refractive index of material is greater than refractive index of mm, refractive index of material of lens is greater than the refractive index of medium, and that medium is not air, that is placing a glass lens into water. So this is the case when the refractive index of air will be smaller than the refractive index of medium and it is less than the refractive index of lens. So in that situation, we see that mu effective, that is the relative refractive index, is equal to mu L by mu M. And if we calculate the focal length, then 1 by f is equal to mu L by mu M minus 1 into 1 by R1 minus 1 by R2. So clearly this term decreases. So if you see here, this term becomes small. So if we term this term as k, then k decreases, and because of that 1 by f decreases, so f increases. So in this situation, the 1 by f is directly proportional to mu effective minus 1 will decrease and f will increase without changing the nature of lens. This is the criteria. If we change this criteria, the nature of lens changes. We will see about it later on. And as the focal length increases, then the power of lens decreases. So in these conditions, the focal length increases, the power of lens decreases. Now we'll see the second case when the refractive index of medium and lens both are same, and in this case the mu effective becomes 1 and 1 by f is equal to 0. So f becomes infinity and the power of lens becomes 0. So lens will neither converge nor diverge. It will behave just as a plain glass plate. Now this is the third case, which is a very important case, that when the refractive index of medium increases, so increases more than the refractive index of lens. So if the condition will be like that, mu a is less than mu lens and it is less than mu medium. Like if I place a convex lens having the refractive index 3 by 2 with respect to air in a medium having refractive index mu is equal to, let's say, 1.6, then in this case the convex lens behaves as a diverging lens and concave lens behaves as a converging lens. That is, the focal length of concave and convex lens changes its sign. So in this situation, mu effective is less than 1 and the focal length is directly proportional to mu effective minus 1. So 1 by f is equal to mu L by mu M minus 1 by R1 minus 1 by R2. So if we consider this term as k, then k less than 0 and 1 by f changes its sign. So 1 by f changes its sign. So 1 by f changes its sign, hence nature of lens will change. So a convergent lens will behave as a divergent lens and vice versa. That is, divergent lens behaves as a convergent lens and opposite behavior of lens is observed. So this is a very important concept, that if we place any lens having a refractive index more than itself, then we see the opposite behavior. And all those things are enumerated in this figure. If you see here, when the refractive index of lens is equal to refractive index of lens is greater than the refractive index of medium, then we see that the concave lens behaves as a concave lens and convex lens behaves as a convex lens. That is, the nature of lens remains same. So here nature same, f increases, p decreases. Here if you see that when the refractive index of medium and refractive index of lens are same, then what we see that f is equal to infinity, power is equal to 0 and lens will behave as a plain sheet. So it's a glass sheet or plain sheet, plain glass sheet. Now we see the third case when the refractive index of a lens is less than the refractive index of medium, then we see the opposite behavior. And for convex lens, the F becomes negative, and concave lens F becomes positive. And this is a very important concept to learn.